Hello, I'm Whitney, and in this video I will be showing you some demonstrations of rotating fluid dynamics. To start out, I will demonstrate how the Coriolis force affects a drop of fluid added to a body of water. To show this, I have a bowl full of cold water, which I add drops of milk in to act as a passive tracer. First, let's see how the milk disperses in still water. The drop disperses more or less isotropically, like we would expect. Now let's see what happens when we add a drop of milk to a rotating bowl of water. As you can see, the drops get stretched out in the rotating water. Let's try to understand why the droplet behaves the way it does. First, let's consider that the droplet disperses isotropically. Now let's put that drop in a rotating fluid. Once the drop is in the rotating fluid, the portion of the drop that disperses radially inwards is subject to a Coriolis force in the direction of rotation. The portion of the drop that disperses radially outwards is subject to a Coriolis force against the direction of rotation. This causes the elongation seen in the last clip. Now I will show how I made topographic Rossby waves using this very simple kitchen setup. Topographic Rossby waves are found on a rotating sphere of fluid, such as a planet or a star. On Earth, these are found around the poles and are responsible for the polar vortex as shown in this image, courtesy of NOAA. The Rossby number is the ratio of effective forces to the Coriolis force, where U is the characteristic velocity, L is the characteristic length scale, and F is the Coriolis parameter. The Rossby number is small at the pole where Coriolis forces dominate, and it is larger at the equator where effective forces dominate. To emulate the Earth, I add cold milk to a bowl of hot water. In the first trial, I add the milk to a still bowl of water. I add it to the center of the bowl and add the milk at the bottom by using the syringe. As you could see in the last clip, the milk spreads out evenly across the bottom of the bowl. Now let's see what happens when the water is rotating. As I let this clip play a second time, you can see the topographic Rossby waves as the sort of wavy edge of the patch of milk. These waves move with the rotation of the water and evolve over a relatively longer time scale than the motion of the fluid. While it's a little hard to see in this video, the milk is also no longer constrained to the bottom of the bowl. Thanks for watching. I would like to thank Dr. Jean Arnaud and the UCLA Spin Lab for their videos about planetary fluid dynamics. These videos helped inspire my demonstrations. I would also like to thank Ben Brown for his thoughtful feedback on this project.